examples of data transformation. So hopefully you've watched the theory one already, and today we're going to go through two relatively long examples. Our first example is here. We're looking at pressure and volume. So some sort of gas problem, and our question tells us to use a reciprocal transformation on volume and determine the equation line of best fit. Now, reciprocal transformation on volume. Alright, is the key part here. Reciprocal, meaning 1 over, and volume being on the x-axis, we're looking for a 1 on x. So we're going to transform the x value 1 on x. Alright, so let's have a look at what this looks like in terms of a scatter plot first, and then transform it. Volume, pressure. We want here volume, and on this axis, pressure. Alright, so relatively smooth curve. And if we look at the circle over here, we can see that this is the curve. That's the curve that matches this one. So we could either log x, log y, reciprocal of y, and reciprocal of x. Now this is important because any of those would help transform the data to be linear. The question has told us to make a reciprocal of the volume, so we are doing 1 on x. Alright, so how do we actually do that in the calculator? Go back to our table. We want reciprocal of volume. Now what you name it is up to you, as long as you can identify that that's the reciprocal of the volume. Then we say, well, I want this to be equal to 1 over volume. That means that this entire column will take the A column and do 1 on. So 1 on 29.5 is equal to that. 1 on 20, unsurprisingly, is equal to 1 on 20. And if there's a mix of decimals and exact numbers here, it doesn't matter, because we have our values. Alright, so let's see if that linearizes our data. So instead of volume here, we want reciprocal of volume, our volume. Oh, that's nice, isn't it? Straight line, it's a beautiful thing. Alright, then determine the equation of the line of best fit. Alright, let's give me some space to do that. So, we want a line of best fit, and we're always going to plot our linear. Regression, show linear. We might just grab that and bring it down here. So, we've got this, but that won't get you the answer. And I can't stress this enough. Y equals yada 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 will not get you the answer. Because Y doesn't mean anything, really. Pressure. I'll do it in the other. Pressure is equal to 12.6186 is equal to 2499.18. And typically, they would ask you for a certain number of significant figures here, so you wouldn't have to write them all out. And then this is multiplied by not just x. I realize it's the x-axis, but we've transformed the x-axis, so now it is 1 over x. And it's not x anymore even, it's 1 over volume. So a little bit here, and there's lots of ways you can lose marks. You can lose marks by leaving them as x and y. You can leave marks by forgetting that you've actually transformed the data and forgetting to write the transformation step in here. Once you've got that equation, it makes your life a little easier for making predictions. Alright, so find the expected pressure when the volume is 5 mils. Is it a reliable estimate? Alright, let's find the expected pressure first, and then we'll consider whether it's reliable or not. So, this here you would type in pressure is equal to 12.6186 plus 2499.18 times 1 over 5. And give me a sec while I work that in the calculator. Alright, so pressure equals 512.45. Now, considering whether this is reasonable or not, we need to use one of two keywords. So let's go back and look at the original data. Original data would be pressure v volume. And we're asked for what will the pressure be when the volume is 5 mils. Now, volume here is 12, so we're asking for volume at 5 mils, which is off the graph here. Well, it's not off the graph, it's hidden in here, but either way, it's beyond the data. So we would say not reliable, and this is a word you must use, extrapolation. By all means write a sentence, but if you write a sentence along the lines of, it is not reliable because it's outside the field of data, frustrating enough, you won't get the mark. You must write, it is not reliable because of extrapolation. You must use extrapolation. Alright, expected volume when the pressure is 150 kilopascals. Alright, so we grab our equation again, here, and what we're going to do is, we are not given the volume, we need to find the volume. So very simply, we put 150 kilopascals will be equal to 12.6186 plus 2499.18 multiplied by 1 over volume. Now, we don't know what volume is, so what we're going to do is we have to solve for that in our calculator. Solve. Well, that worked out nicely, didn't it? Comma vol. 18.919. So here our volume is equal to 18.19. Now, is that reliable? Well, we're talking about something that's 150 kilopascals. So let's go back and look at the original data. 150 kilopascals in pressure terms is about here. And that is well within the data. So our answer would be yes, reliable, keyword here, interpolation. Lovely. Now, that's that example done. It's about transforming the data using the correct transformation and then using the equations to predict correctly. Sorry, that's gone for quite a while. Here is video, well, I won't make a separate video, I'll just make this one long. This is another transformation question. If you're comfortable, then have a shot on your own. Otherwise, feel free to watch this. Alright, seeds of successive sunflower arranged for a compact head. Counting the number of seeds in each successive circle starts to center moves outwards. You might recognize this series of numbers here. It's extremely famous. Google them, they're cool, really. Alright, A, fit a least squares regression line and plot the data. Alright, let's go to where our sunflowers are, sunflowers and seeds, and we are going to do circle here and number of seeds here, and we have data that's, well, not linear. That's fine. And find the correlation coefficient. So remember, correlation coefficient is R. And to do this, we go back to the original data, go menu, statistics, stat calculations, linear regression, and then we want our X list to be number of circles, our Y list to be the number of seeds, and then we click OK. And our R value is 0.87. So 0.87, what does this mean? It means there is a strong positive correlation. Using the regression line for the original data, predict the number of seeds in the 11th circle. Okay, so that's that there. Really, we have the regression line equation here. But if we want to see it, and I quite like seeing it, we can plot another one. There. Let's grab that. So that's the regression line. Now let's try and calculate the number of seeds in the 11th circle. So what we would do, we'd write it in terms of its variables first, but to save time here, I'm going to go negative 59.0677 plus 21.7394 times 11 is 180. So our prediction for the number of seeds in the 11th circle is 180. Which, to be honest, is a fairly terrible prediction because the 10th circle has 233, so 180 is, well below what we would expect. Find the residuals, plot the residuals on a separate graph. Are they linear? Alright, so the residuals here, analyze residuals. They're the residuals plotted on a separate graph. Are they linear or evenly scattered? No, they're not. What type of transformation could be applied to the x values? Alright, well our curve looks like this. I might just get rid of everything else. What transformation could be applied to the x values? Well, to figure this out, we go to our friendly transformation circle and recognize, well, the curve looks like this. So the transformation could be applied to the x values is x squared. We could square the x term. It's an x squared transformation, and the reason is it stretches the x values, the higher x values. Alright, what transformation can be applied to the y values? Well, go find this again. Either log y or reciprocal of y. Log y or reciprocal of y. Why? This shrinks or constricts, choose your word, the higher y values. Alright, so they're the three options that could work for us. Alright, apply a log y transformation to the data. Fit least squares regression line to the data and plot it with the data. Alright, so here's the original graph and the original data. Now we want to do a log y transformation. So that's the x, the y, we'll go log seeds equals. This column here will be the log. Note how it goes from italicized to ordinary letters when it recognizes command, log seeds. And seeds is bold because we've used it already. And what's happened here is it's taken the log of 3, log of 5, it's done some fancy algebraic terms to simplify it, log 8 into 3 log 2, don't worry about that, and so on. So it's done what we expected, basically. If you wanted to convert to decimals, then you can change the calculation mode to approximate. Alright, but instead of seeds, we now want to look at log seeds. Pretty nice. Alright, now, what was the rest of the question asking? It was asking to fit a least squares regression to the line and plot it with the data. Alright, so let's plot a least squares regression line. Nice. Find the correlation coefficient. So correlation coefficient once again is R. And here, we're going to have to do the same stat calculations, but this time instead of the y values, we're going to use log y. X values is still circle number, y values is log seeds. We want to overwrite the original data we had. So now the R value is almost 1. It's perfect. Why? Why is it increased? Because the data now fits the straight line more accurately. There are far fewer residuals. So our least squares regression line fits the line much more accurately because there are less squares. Like if you imagine those squares that form off the points, there are fewer of them because we're almost exactly on the line. Alright, complete a least squares regression for the transformation. And remember, that again will not be our answer. Our answer will be log seeds is equal to, so we haven't just written y, we've written log seeds is equal to 0.274, I'll round it to 5, plus 0.209 times, now not x, but circle. Alright. Calculate the coefficient determination. Coefficient determination is r squared. R squared is basically 1, which means that, what does this explain? That means that 100% of the variation in seeds is explained by variation in circle number. Using the regression line of the transformation, transform data predicts the number of leads for the 11th circle. Alright, I'm running out of time here because class is about to start. You would take this value here, and what you would do is you would substitute this into your calculator. I wonder if this will let us do it. Except here, we're going to solve for the number of seeds, x. Given the 11th circle, we're going to say solve, comma, x. So that way, we're asking the 11th circle here, we replace it with 11. X we want to know, and we're going to find it by doing that. 374. Now, 374 is a much, much better prediction than the one we made from the previous question. Alright, sorry, that's a record video for me. Well done if you sat through it. If I were you, I'll tell you in class to break it up into 2 parts. Thank you very much. Bye.